Lab4 here, we have our clock module. This is how we count up for the 100 megahertz clock, and we then output seconds, minutes, and hours as 6 bits for seconds, 6 bits for minutes, and 5 bits for hours. So as you can see, we begin by setting the clock back to each individual element to 0. Then we have an always block here that always ticks at the 100 megahertz clock, and we always count up +1. This statement here is if we have the set time state enacted, then the clock will take in those values and start counting from the set time input. Otherwise, the clock counts up to 100 million. Once it gets there, resets the count, adds 1 to seconds, and does the typical math for doing seconds to minutes and then minutes to hours and resetting those as needed once they hit 60.
This is our finite state machine, and the way it works is we have 8 states that is able to cycle through. So how it works is when the default state is the time clock, and when the user first presses the button and they're holding it, it would go to the wait state 1, and then it's going to stay there until they release the button. So when the input goes back to 0, and then it's going to go to set time, and that's going to repeat for wait state 2. So they're going to press a button, and until they release it, they're going to move to set alarm, and then again it's going to go through wait state 3 and then set time format. So the key is that we wait till the user to press the button and then release it to move on to the next state. And so that's a big overview of how our state machine works. And then this is just a case statement of how we did that in practice. So we just had the default state of time clock at 00. And then if the input goes high, then we move on to the next state, or else it'll stay at the same state. And we use that same logic for all these different case statements. When it's high, you move on to the next one. If it's in like wait state, or if it's time clock or set time, and if you're in a wait state, when it goes low, you move on to the next one. And so that's how our finite state machine works in this case.
Unfortunately, due to constraints, my lab partner and I were not able to push the final portions of the lab, set time, set alarm, and set format onto the board. However, we do have waveforms to confirm that our code does work. So I'm going to give a brief overview of how our Lab4 works, and in particular our state machine. So here you can see we have a state button that when pressed, it goes high, and when released, it goes low. And you can see we have a state LED that when the button is pressed, it goes to the first state, and then when it is released, it goes to the second state. So what we did was we made wait states in between each of our actual module states to simulate the button being pressed. So when the button is pressed, it goes into wait state 1, and once it's released, it then goes into the actual set time module, which is state 2 of all the states. So for this set time module, I have some input here. So what we have is the input for the binary representation of 12. And as you can see, this is the in time format, and it goes and sets the leftmost digit of hours to be 1 and the rightmost digit of hours to be 2. And as you can see, we then press the next button, which cycles to the next time that you want to format. So in this case, it would cycle to minutes. We then set that to 0, so the minutes still remains as 0. And then we hit the next button once more and release it again. And we then set the binary representation of the end time to 45. And as you can see here, the seconds left digit turns to 4 and the seconds right digit turns to 5. Here we have the set alarm waveform. So like I explained before, we have the state button is pressed, which sends it into the first wait state. It's released, which sets it into the set time state. Pressed again, another wait state. And when it's released again, it gets put into the set alarm state. So now that we're in the set alarm state, I go ahead and I hit the next button, which cycles us to minutes. Then I hit it again, which cycles us to seconds. Now for simplicity's sake, I set the seconds equal to 1. Since the waveform shows us the nanoseconds of the clock, I thought it best to just do 1 second. And also I decided to pull back how quickly our counter counts. So now instead of it counting once every 100 megahertz, for every 100 million ticks of the internal clock, it now counts 1 for every 1,000 ticks of the clock here, so that we can see everything on the waveform here nice and clearly. So what I did was I went and I took the in time format and I went and I set it equal to 1. So now there's a register that is storing this value of 1. I can go ahead and zoom in here. You can see our second least bit here is equal to 1, and that gets stored in a reg. And as you can see, our 7th segment is displaying that 1 second. Now what I do is I then go ahead is once that 1 second is stored, I go ahead and I hit the state button again, release it, and hit the state button again, because we need to cycle through the set format and then cycle back to the original clock state, which is state 0. As you can see, we're back at state 0. And you can see we haven't fully counted up to 1,000 nanoseconds yet, so the clock is still at 0. And as we let the clock go on, as you can see here, once we hit 1,000 nanoseconds, the clock tips over to 1, and then our LED that we designated as our alarm goes high. So the reg and the reg that was storing 1 is now equal to the clock's time, and it is signified by the LED going high and turning on.
So we set the button to high, and then we let it go. So now we're in set time. And then we input the numbers 23 for in time. And this switches the hours most significant and the hours least significant to 23. And then we press the button again and then release it. So now we're in set alarm. And then we press the button again and release it. So now that we're in set format, which turns on or turns high M, and then that turns high PM. And then that in turn switches the hours most significant and the hours least significant to 11 to signify that we're 11 p.m. As opposed to 2,300 hours.
For Lab 4, we found one of the more difficult parts of this was we decided to write more modules and link all those pieces together. And while it did help with troubleshooting to find exactly where the issue was, in particular in which modules, we found it difficult to make sure everything connected properly and was displaying what it needed to by the end product.
And for the finite state machine, one thing that we found difficult was that it was a new way of writing logic. This is something that we haven't done in previous labs. And just so getting to know how to write that properly in Verilog and then making it work with the other model that we had was quite difficult. And yeah, that was the definitely difficult bit, was making that finite state machine work.